This is Web Dev Sumos, and today we'll be solving questions from trees for our tree day. Yep, that's what we'll do. We'll start with an easy and then go to a medium question. And that's how we'll roll, and let's see how we can do today. Okay, so this is the first question, which is convert sorted array to binary search tree. Got it. So the question says, given an integer array nums, so the question is 108 convert sorted array to binary search tree. Okay, got it. So I understood what the problem is. Given an integer array nums where the elements are sorted in ascending order, convert it to a height balanced binary search tree. Height balanced binary search tree. Okay, I see. I see what is going on. So my nums is -10, -3, 0, 5, 9. Height balanced binary search tree. So how should we go about um, how should we actually go about doing this one? So everything is sorted with me right now. Okay, everything is sorted, but what I have to do is I have to zero -10. So height balanced is both the right and left should have the same height, right? That's what they mean by it. That's what is going on. Okay, so let's see if the array could be null, or array will have always one element in it. Okay, nums array is sorted in strictly increasing order. Got it. So how like what is the first thought that is coming to my mind once I see this question? Like the can I how can I traverse this array and get to the uh, like how even I can start with my root node? Like that's the starting point, right? So how will I start with that? Like, so obviously what I feel is my tree will be always balanced, right? Tree will be height balanced. So what I was thinking is my root would be always always in the mid, right? That's what I'm thinking. Mm-hmm. So the length of this is minus was 1, 2, 3, 4, 5, and this was of length 2. So I believe that we have to divide them into divide and conquer. Using divide and conquer technique, we have to come up with a solution. um, or am I over engineering it? Or else, like, there is no way of us finding the what would be a root node. Okay, or if we straight away go and traverse this array. Let's say if we traverse it, then -3, -3, 9. Okay, no, that wouldn't be the case. This is binary search tree, right? Binary search tree. So what I'm thinking is, let nums, so if nums dot length is less than equal to 1, or if it is less than equal to 0, let's say, then we have to return null in that case. And if, what do we have to convert it to binary search tree? I guess we have to return the head of this. And what I have to do also take care of is, if nums dot length is less than equal to 1, return nums of 0. Okay, that would be my base case. And what else do I want to do? So I want to make I want to calculate the mid of it. Let mid is equal to math dot floor. I want to, first of all, I want to take the left is equal to 0, right is equal to nums dot length -1. So yeah, that should do it. And then left plus right by 2 should give me the mid. And once I get the mid, what I'll do is mid equals to math. Yeah, I want to make that mid root. So in this case my mid would be 0. So new tree node, whatever the nums of mid is, the mid pointer is currently pointing at yeah, the value that mid pointer is pointing at. We want to create a node for that, and let root is equal to this guy. And then what I want to do is root dot left is equal to whatever is on the left hand side of it. I want to return new tree node nums dot slice 0 to mid -1. Okay, and root dot right is equal to new tree node nums dot slice 0 to mid +1 to the end, till the end, hopefully. So I'll just take this array and see if I can get those values, like my mid. I always forget like how the mid and everything would be working. Hopefully this is visible to you guys. And then let arr is equal to, I'll paste this array, let mid is equal to math dot floor, let 0 plus arr dot length -1 divided by 2 should give us the mid. Yeah, mid is 0. Then arr dot slice 0 to mid -1 0 to mid, and add dot slice mid plus 1. Yep, mid plus 1 is right, but mid minus 1 is not right. So this will basically give us what we are looking for. And once we are done with this, we have to basically return our root. Okay, so that would be it, right? So we'll go for 0. So let's try it on this. We'll go for 0. We'll create the root for it. Then for the left side, we'll go for this guy, and then we'll be traversing this thing. So 0 length of 0 plus 1 by 2 is 0.5. Flooring it would be 0. So this guy would be our root, but there is nothing on the right hand side, so we'll be returning null for it. And yeah, returning null for it. And for this and for the right of minus 10, we'll be returning minus 3. And okay, let's give it a run. Let's see if this passes. Oh, sorry, my bad. I shouldn't have done this, but instead I should be doing sorted array to BST. Yep. Yeah, instead of new tree node, we don't want to do tree node here. We just want to recursively call this guy to BST. Yeah, that's what we want to do. Val is equal to 0, left is minus 10, left is null, right is null, right is 5, left is null. So I'm returning a tree node, right? That's what I'm returning. Oh, okay. Oh, new tree node. I also have to make this new tree node, right? And here also new tree node. So should it be undefined, or how is it like? Let's see if this works. Okay, yeah, that does work. So for these two cases, cool. I guess for even one node it will work. Okay guys, it worked. So our logic of doing this was right. We'll be always traversing both the nodes, both side of the array and traversing it accordingly. So basically the time complexity of this would be I guess we are traversing the entire node, the entire tree, like dividing it in half and then traversing. It should be O of n, but we are always branching out in two ways. Will that affect anything? And I guess at any given point we'll be always using the height of the tree. So of n of h would be the height of the tree. So space complexity would be that, and what should be uh, the time complexity. I'm not so sure about what the time complexity would be, but we can obviously go to the editorial and see what the time complexity is for this one. Yeah, time complexity is of n. Okay, log n. Got it. Log n, because we are um, halving the, like we are dividing the array into two parts, and we'll be always having the half of the array always in the stack, recursive stack. So yeah. So I believe this was the approach that we did. Okay. Cool. So they on also using the pointer, this could be done, but instead we sliced it. So this would be a better approach of doing things. Let's see what pre-order traversal. Always choose right middle node as root. So helper left right, which construct a BST from nums element between index left and right. If left is greater than, there is no element available. Okay. P, if left plus right is odd, add 1 to P. Okay, initiate the root, then recursively left P minus 1, P plus 1. Always choose right node as a root. So even if we divide it and left plus right, mod 2 is equal to 1 if it is odd, and plus P. That is basically doing the same thing, right? Choose random middle node as root. Okay, yeah, this is a pretty tricky question to be put into what do you say, in a easy bucket. But yeah, oh, this was the first time we solved it, and for this time I did not see any solution video for this one. solved it by my own. Good job. So yeah, this is just a note for myself if I come across this solution, this question. So just a boost in the confidence. LeetCode is like very unpredictable. Some days you're doing just fine, and the other days you even struggle at easy questions. Just it's a reminder that I solved it by myself. So let's put this. Oh, what the hell? Okay, let's put this guy into the binary tree. Where are trees? Yeah, let's put that in the tree section, tree bucket. So this is okay, and the companies that have been asked this question, like for 6 months to 1 year, Amazon. This used to be their good question, but nowadays it's not been asked. So still, I'll star mark it, and yeah, just check mark it, and then we can go and see in this medium question, insert into a binary search tree. Let's do this one. Let's sip some water before you get started. Okay. I guess have I solved this question earlier? Okay, I don't care. I'll see this question as a new question and not. Okay. So you are given the root node of a binary search tree and a value. Sorry guys, I lost. I was thinking about something else. So 701 insert into a binary search tree. The question says you are given the root node of a binary search tree and a value to insert into the tree. Return the root node as return the root node of the BST after the insertion. It is guaranteed that the new value does not exist. It is guaranteed that the new value does not exist in the original BST. Okay, everything is unique. That means notice that there may exist multiple valid ways for the insertion. As long as the tree remains a BST after insertion, you can return any of them. Okay. So this is a good question where 42713. Okay, I've been given a root node. Okay, so that is my root, and this is my root. So that there would be many edge cases, and I have to treat every every subtree as a tree, and then check for the value given value if it belongs to that very position or okay. So let's say phi is given to us. We'll check if phi is greater than 4 or less than 4. So phi is greater than 4. We go inside the 7. We check if phi is greater than 7 or less than 7. Less than 7. So we go to the bottom. Okay, got it. So this is just one edge case. Let me go here, refresh this guy, and I can open up the Miro board. Oh, my iPad has just died, so no way of resurrecting it right now. Hey, yeah, Still grinding that lead code. Are you two grinding the lead code, or how is it like? Okay. Okay, so we have this. Let me just shift this a bit. um is there a white color? If I put f, oh sorry, f, it's showing red color, but f should be white, right? Okay, let's take yellow. That is always the best. um so I have this. If suppose, let's say, one comes in. So I was just wondering the edge case where we have, where the element should be placed at the root. But okay, yeah. So I guess I believe that we will be always going to going to the leaf, irrespective of, there won't be a time where we'll be inserting that very particular node to the head of the root or head of the tree at any given point. So we'll be always going to the leaf. So that's what I believe is happening. So let's say if we have this tree, this would be -10. Okay, this would be 2. And if let's say -1 comes in, and we want to insert this guy. So this is smaller than this one, so we go here, and -10 is so -1 is greater than the -10, so we'll put this guy here. So that makes sense to me. So I believe that we'll be always traversing down the leaf, and once we reach the null, once we reach the null, what's wrong with my camera? Okay, yeah, once we reach the null, then basically we can insert um, this guy there. Isn't that what's happening? Yeah. And basically start returning back whatever we did, and finally we'll be returning the head of it. Yeah, we have to return. That's what they said, right? Notice that there may exist multiple valid ways for the insertion. As long as the tree remains a BST after insertion, you can return any of them. Okay, so I believe that that's what we have to do. I don't know why I wrote this line earlier, and why is it still here. I'm not sure. Okay, let's see if our if what would be the edge case. Will I be getting all the time there will be a head, or there won't be a head? So the number of nodes in a tree will be ranging from 0 to 10 raised to 4. So looks like we won't have a node in our tree. So the base case would be, if our root is equal to null, then basically the value that we have been given, we have to create a node out of it and then return that thing. So let's write down the edge case. If root is equal to null, then we can't do anything else rather than just returning the tree node with the value that has been given to us. That's what we can do. So that is the edge case. Okay, so let's see how we can traverse this. Basically we can traverse this using, I always like to do it recursively, so that makes the process easier a bit. um, so we have our root with us. Okay, what we have to make sure that we go to the leaf. That's what we have to make sure. So let's say if root is not equal to null, and we are good to see what the value, if it is greater than or less than it, then if root dot val is greater than the value given to us. And wait a minute, should I be worried about greater than or equal to at this stage? If it is even, okay, so they said it would be distinct and there will be no values, so I won't worry about this. I will just say that root dot val is greater than the value val. Then I will just insert in I will call insert into BST root dot left okay. So wait a minute, where at what point will we insert this node? Like this should be going somewhere, right? This, okay, yeah, so this should be going somewhere. So instead of I'm just saying looking at this fact that we have to traverse the root dot left, right? Because that's where it belongs, in the left, because it is less than the root value. Yeah, but mm-hmm. So should I just check if no. So what I was thinking is, can I do this root dot left is equal to this, and just keep going ahead, else if it was less than root, if the root dot val was less than the value that we have to insert, then basically we have to go to the right side of the tree into BST root dot right. Okay, that's what we have to do. Okay, so once we are done with this, then we can just simply return the root. Is that, I don't think so this would be that simple. Root is equal to, so I have my root with me. Let's do a traversal. So I have a root with me, then what is the value? Okay, the value is 5 to be inserted. I see that the value is greater than the root node. Then I go to the right side of it, and then the right value is then compared with the value, but at this stage the 5 is less than what the root value is, so we go to the left of this, but the left is null. We have reached null. We create that t node and return it as a value, and then the root dot left is assigned to this guy. Then this root is sent back. Okay, yeah, that basically makes sense to me at this stage. And let's try run one more thing. Let's try run this. Oh, okay. Another accepted tree is you basically replace. Yeah, that can be also done, but my logic is like I will always go to, instead of balancing the tree and replacing whatever at is at the head, doesn't make much sense to me. I will just keep going to the bottom to the leaf and then insert it where it belongs. So let's run this. Okay, everything is wrong. Why is that? So we did insert a node, right? A tree node and value. So output is 42713 null 0. What was expected is from me was okay. That's what happened, right? Root dot left is equal to new tree node. I assigned it with the val, but this didn't. Why did not this didn't work out? Why did this not work out? Okay. Like what I might be missing here. Return new tree node. Like, is my way of thinking wrong, or how is it like? I'm always going to the root and then returning the root, whatever the root is. I'm returning that once I've assigned it. Let's see, let's console.log the value of root. So okay, so what happening is 7 is null, but that's what I did, right? Tree node I okay. So the thing is, it would be going into the insert into BST root dot left. So that's what I did. So I just want to see what insert dot root returns back. Let node is equal to this guy. Let node is equal to insert. Sorry, I'll just copy paste this. I guess at this stage I might have bombed this thing in an interview. So console.log, let's print out what node was returned to me. Left right, and then root. Okay, So let's run this guy and let's see if what we get from it. Oh, sorry. I am doing it a lot of time. So node. Okay. Root is equal to 0. Root dot val, if it is greater than value, the val that has been given to us, the val is just a number, so if it is greater than that, yeah, if it is greater than the val, then I have to go to left. That's what I did, right? But this is, let's say we have return console.log reached leaf creating tree node 5 val, whatever val is. Okay, yeah, we reached leaf, then oh, okay, that is what is happening. Okay, I didn't pass val, so that is what was happening. Okay, now I get it. Okay, this is accepted. Cool. Wow, so this was because of a silly mistake, I did not pass the root there, and that's why it was failing. Otherwise it was done a long back. That is my mistake, and it shouldn't happen. You should be alert in that case. Okay, no worries. Let's bring this guy back to its original form. Let's remove everything. Okay, we have removed everything. Now the only thing is we need to test this out. Let's run this one more time, making sure everything runs. Okay, yes guys, this is working. So this seems pretty easy, but I guess there might be follow-up questions that the interviewer would ask. Yeah, so I'll see what those are, but right now I guess we are running out of time. So yeah, like a good start for the day, and then we can keep solving questions, and let's see finally. So the time complexity of this will be always halving, right? We are going half. So log n would be the time complexity of this, and space complexity would be let's say height of the tree. Yeah, like whatever the height would be, that would be. Oh, so not a lot of companies ask this question. Amazon just asked. So but anyways, we'll add this to our list of questions. Add this, and let's see if we have ever solved this question, or was it the first time. So yeah, looks like we have solved this question in March of 2023, and I might have seen a solution. Solve the question by myself using DFS recursive approach. Okay, so that is what it is. Okay guys, that is it for this one. See you in the next stream. Till then, take care. Bye bye.